So thank you very much for joining to this session. So my name is SeongJae Park, and I have a preferred name SJ. So I prefer to be called just SJ. So please feel free to call me SJ. I'm working for Meta on kernel team in Meta for servers. So today I want to share about some introduction of DAMON and its new recent features for auto-tuning its monitoring intervals. So long story short, what I want to say today with this session is please try DAMON again if you have disappointed before with new feature called monitoring intervals auto-tuning. So let me introduce DAMON and some of the control and auto-tuning features first. So DAMON is basically a kernel subsystem for data access monitoring. To say that, I think we need to first say about what is the data access is. It can be defined as event on time and space of the memory. In this slide, the right side is showing a access heat map. That is, the x-axis is showing the time, and y-axis is showing the address on the memory, and the color is showing how hard or how frequently the address of the memory on the time was frequently accessed. The bright one is more frequently accessed one, and darker one is less frequently accessed one or not accessed at all. So if we show a very small portion on the heat map in a bigger scale, then we can show something like left side. And when we try to do data access monitoring, we try to do that because the memory is expensive, and therefore having memory be equipped but not accessed frequently is just a waste of the money and the time. And what we hope at doing the data access monitoring is that we want to do that in precise way for every bit and be complete about the monitoring by keeping all the information for every moment, and also very lightweight so that we can run that on production. But the reality is that it is very expensive, and you ain't gonna need every bit of every moment of the information, and therefore we have started developing DAMON that is providing controlled and auto-tuned trade-off for making reasonable and practical monitoring only. So first, we want you to make the space more controlled at monitoring. For this, we introduced a new concept called region. It is defined as a sub-area of the memory space and time. It is a collection of adjacent elements on the area that having similar access pattern or access frequency. And this means that by the definition, we don't need to check every bit access on the same region, because every element of one region have same access pattern, and therefore we can do access check of only one element per region, and then we can say that all the elements in the region was accessed or not. And therefore, the very naive version of the prototype of DAMON was fixed space-time granularity. And this can be thought of like a sort of periodic fixed granularity idleness monitoring, which is motivated by the idle pages tracking feature of Linux kernel, which was existed before DAMON, still existing and very useful. And nevertheless, anyway, by utilizing this scheme, we can reduce the time overhead to divide it by the space granularity, and also reduce the space overhead to be divided by time granularity. That is, we can control the overhead with the fixed granularity of space and time. This is already very controllable, but still the overhead is ruled by the memory size and the total monitoring time, and also the accuracy of this scheme would be very poor because the granularity is just fixed. And therefore, we slightly improved this scheme by making it to capture not only 0 or 1 access frequency, but n access frequency. That is, just adding a per region counter and then count the sampling access check result as it goes by. For example, as time goes by, we will check the access to each region in every sampling intervals, and then increase the per region counter based on the research, like this. This means that we can now reduce the space overhead to 1 per n. The n is the maximum access frequency. Nevertheless, still the overhead is ruled by the memory size, which is not always controllable by ourselves. And therefore, we further introduce auto-tuning of the space. Major problems that we have found so far with the fixed space granularity is that adjacent regions of similar hardness are just waste of the resource, right? And also because the granularity is fixed, we cannot do more fine-grained space monitoring finer than the fixed granularity. Sometimes we want to do that with very fine-grained granularity like page granularity or even bit granularity in future maybe, but we cannot do with the fixed granularity. And therefore, we introduce an auto-tuning of the space granularity. That is, it is auto-tuned dynamic space granularity. The mechanism is very simple. Just repeat merging regions that are adjacent and having similar access pattern because they are just waste. And then randomly split each of the regions because the access pattern could be changed or our merge of some regions was not a wise decision after some of the time goes by. As a result, as sufficient enough time goes by with this scheme, then the number of the regions becomes same to the number of real different access patterns, which is very reasonable in a way. And also, we further provide a knob for setting the minimum and maximum number of total regions after this merge or split to be specified by user. That is, we do auto-tuning, but still provide a controllable knobs for safety of the minimum and maximum cap of the overhead to users. That is, users are still having the control for safety, but inside the user-specified range, DAMON can do automatically tune for minimum overhead and maximum accuracy. As a result, the pictures that users will show will look like this. No more wasted regions. And as a result, the time overhead becomes the minimum of the different real access patterns and maximum number of regions that user specifies. And therefore, it is no more ruled by the memory size. It doesn't matter if the memory size is 100 gigabyte or 1 terabyte or even 1 petabyte. It is ruled by not the memory size, but real different access pattern and the user-specified maximum overhead. And accuracy becomes the best effort high because the auto-tuning will find real access pattern as much as possible, at least if enough time for converging has given. And therefore, the granularity can be finer and can go down to even bit-level access in future. Current implementation is making a minimum limit as page size, so we cannot do the bit-level access with today's DAMON, but in future, who knows? And we were finding that there could be some more rooms to improve, that is time granularity problems. That is, we have defined the region as a sub-area of time and space of the memory. That means region is not only about the space, but also the time. And from that perspective, from this heat map, we can show some inefficiency in not only space, but also time axis. There are multiple time adjacent regions of similar hardness, as like those for space axis. These are also just only waste. And therefore, we introduced a dynamic time granularity feature, a little bit different from the dynamic space granularity, but the mechanism is very simple. Just add yet another counter per region that counts how long the current hardness of the region of the site has kept for how long time. And then, for example, on this heat map, for example, if this is the time, the age counter would be look like this. Age is the name of the counter, and it can increase if the access frequency has continued or reset, and therefore, as a result, each of the snapshots contains a sort of history of useful length. That is, as long as the access pattern of a region was kept for a long time, we can know how long the access pattern has kept. If it has changed, then we don't know the information before the significant change of the access pattern on the region. However, who cares about the past that already changed? So this can be a kind of reasonable amount of information, in our opinion. As a result, we can get the snapshot as the real output of DAMON. It is order of maximum number of regions, time, and space overhead. Not only space, also time, space, overhead. We don't need to record all the snapshots for all the record time, but we just need to get the latest snapshot. Then it contains all the reasonable amount of time information there. And therefore, both time and space axis overhead are no more ruled by the memory size or monitoring time or the runtime of the workload that we need to monitor. And where we can use this, basically just fun for showing something funny patterns, but also it can be very useful at profiling the access pattern of your systems and workloads. Based on that, you can make some profiling guided optimizations, like finding hot pages in the workload and protecting those with MLOX system call who are using huge pages or proactively claiming cold pages. Actually, we have tried this in a prototype and was able to show 2 times performance improvement on a very artificial environment. It was just very artificial test environment, though. Please note that. Nevertheless, from this point, we started thinking about, OK, then we can let application programmers to use DAMON to understand their workloads and optimize their program by modifying their source code. But why not let kernel just do this? Because kernel already have this information, and kernel has the privileges to the memory management actions by itself. So unless it is really required to have some user space help, kernel can do that, most of that on their own. And therefore, we have extended DAMON for not only for data access monitoring, but also access-aware system operations. We have expanded DAMON with a new feature called Data Access Monitoring-Based Operation Schemes, or DAMOS in short. This is actually another half of the DAMON now. It allows users to define system operation schemes based on access pattern. Users can specify what access pattern of regions they have interest and what memory management actions, such as reclaiming those or keeping in DRAM or using huge pages or migrate to faster NUMA node or migrate to slower NUMA node like actions. Such a scheme can be specified by user and provided to DAMON. Then DAMON will continue monitoring of the access pattern and periodically find the memory regions that are eligible to the user-specified access pattern and make the memory management action to the regions. It makes sense, right? But in reality, in production, we found that the finding optimum access pattern is very challenging, especially when it is a dynamic environment. Some hyperscalers or some people who have time and money could do very exhaustive profiling of their workloads and understand how they work and find optimal access pattern of the scheme. But it is difficult for normal people, and also when it changes, it is very challenging. And therefore, we have implemented a few features for safe control and auto-tuning. The first feature is called DAMOS filter. This is for fine-level specification of the DAMOS target regions. DAMOS target regions can be specified by access pattern. Access pattern is good information, but not enough to be fine-controlled, because there are some more information that users can know about. Yes, we want to do reclaim cold pages, but we want to do that for only file-backed pages or only anonymous pages, because we have some fast swap space like CSwap. That could be very different. There could be such a very complicated and different use case, and therefore we allow users to define the DAMOS target memory with not only access pattern, but also non-access pattern information, like page level information, like whether it is anonymous, file-backed, which C groups it is owned or not owned, and if it is currently backed by a huge page, or whether it is currently in LRU active list or inactive list. And also, we can specify the address of the region as a condition. For example, we can ask DAMOS to page out cold pages in NUMA node 1 that associated with C group A and file backed. And also note that this can also be used for monitoring feature. That is, DAMOS is basically for memory management action, but it also has a special action called stat, which can be used for not making real some memory management action that can change something, but just reading the found regions. And therefore, this can be useful for page level monitoring too. The second and slightly more important, in my opinion, feature is called DAMOS quarter. So to utilize DAMOS very well, you need to specify 6 parameters by default: the range of minimum and maximum size, access frequency, and the age of a region. That is, how big the region is, how frequently the region is accessed, and how long the access frequency has kept. Controlling something with 6 parameters is not a very easy thing. And we have DAMOS filters, and DAMOS filters are more deterministic and therefore easier to use. But anyway, the 6 parameters, this is the origin of the problem, in my opinion. And sometimes just setting threshold flexibly, just naively, say when we want to make some actions for cold pages, we can just make the coldness threshold at not accessed at all, just for 1 second. That could be too much, but if we can control the aggressiveness of the DAMOS box, then it can be easier to be used and work in many cases. And therefore, we have introduced the quarter feature. That is, the quarter feature sets the aggressiveness limit as amount of the memory that DAMOS can apply given action per user-specified time interval. For example, we can ask DAMOS to page out cold pages up to only 100 megabytes per second using 2% CPU time, up to 2% CPU time. And based on this, under this quarter, when DAMOS find memory regions eligible to apply the memory management action, but if the total size of the region is smaller than the user-specified quarter, then DAMOS can do prioritization of each region based on the access pattern and then apply the action to only the quarter size of highest priority regions. For example, if we found 2 gigabytes of cold memory based on the access pattern that you just specified, and if the quarter is 1 gigabyte, then DAMOS will do page out only 1 gigabyte of coldest page. And therefore, this can work in a common case, in our opinion. Further, we found that this is very effective, but still difficult to set the optimum value of the quarter. And therefore, we have implemented the quarter auto tuning feature. While working with this, we found that we are asking not very good question to our users. That is, we are asking users how much cold pages are cold pages. How much resource could we use? This is a kind of mechanism. This is kind of a question about asking how should we work? Maybe a better question is what you really want to achieve with this DAMOS scheme, the final goal or policy. That is, if we run productive reclamation, we would have some different goals. Maybe I want to keep at least 25% of the system be free always, or just use productive reclamation as long as the memory pressure stored time of the system is under some small, low level to give some healthy pressures. And therefore, this feature lets users to specify the real goal of the quarter as a value of a metric. And the metrics can be several things. There are some system metrics that DAMOS is supporting. It supports precious stored information time, and NUMA node memory utilization, and also it can be some workload latency or bandwidth or transaction per second or whatever. You just can specify some arbitrary metrics on their own and feed arbitrary values for that on their own, or just ask Damon to read that on its own if it is somewhat that Damon can read on by own, like PSI level or NUMA node memory utilization like things. For example, we can ask Damon to reclaim cold pages, aiming 0.5% memory PSI. Then Damon adjusts the quarters using its internal feedback loop based on the current value of the target metric. For example, if memory PSI is 0.1% in this example case, which was aiming 0.5% memory PSI, then it will increase the quarter to reclaim more warmer pages. So what I have mentioned so far is what Damon was behaving until last year. And we recently found that we are missing some more important features that we can further auto-tune, and implemented a new auto-tune feature called monitoring intervals auto-tuning. This is the major topic that I really want to discuss with you today. So after we have made Damon be widely usable, there was some questions about Damon or complaints. People were saying that, okay, we have tried Damon as you have introduced, and what we are seeing on our system is that the heat map visualization looks like just cold, or just hot, or just some random things over the way. That was the frequently asked question. And my frequent answer was that, have you tuned the monitoring intervals? That is, so at the beginning, with the fixed granularity and up to n access frequency monitoring schemes, we have introduced the sampling interval and aggregation interval. Those are set as 5 milliseconds and 100 milliseconds by default. And the people who were seeing unexpected research were using the 5 millisecond and 100 millisecond intervals. Those are not a real good default parameters or suggested ones, rather than that it is just a very starting point that needs tuning. I'm not blaming the people who asked the question, but I admit that this was a very poor decision to just having the two intervals, though that was the best that I could do at the time. That is, let's see why the intervals are important and why missed tuning of those can be problematic. If intervals are appropriate, we can show some meaningful pictures from the monitoring research like this. Like this is just same to what we have shown at the beginning as a fixed granularity time space monitoring with n access frequency. And if intervals are too short, let's say that we zoom in to the real access on time space, and we keep the sampling interval and aggregation interval very short, then everything looks cold, right? In opposite, if the intervals are too long, then everything looks hot, like this. This is the big problem. Maybe someone could ask, then maybe we can just increase aggregation interval, right? And keep sampling interval short. This theoretically can work, but basically, in this case, most of the samples would just return negative results, and therefore it is just unnecessary CPU cycle waste. And also, on large systems, inside the sampling interval, a very similar problem for aggregation interval comes again. That is, we are assuming each of the region has entities that having same access frequency. But if we keep sampling interval very small, we can see accesses that made only within the very short sampling interval. And on large systems, let's assume that there is a 1 terabyte memory system, and we are setting sampling interval as, say, 1 second. And if working set is 500 gigabyte, can some workload really access 500 gigabyte memory within 1 second? Can that supported by common systems? I don't think so, and therefore, in reality, with the sampling mechanism, I think it wouldn't work in real. And therefore, we have found this very lately, and in the beginning of this year, we started to working on making this better. Firstly, actually, I was knowing this is a problem because I also had to do this kind of tuning on my own and help others who were asking the questions. And therefore, we have summarized what we are doing for tuning and made it as a guideline. The guideline is very simple. If the heat map looks cold, just increase the intervals. If it looks too hot, decrease intervals. And when you do that, change both sampling and augmentation intervals in same ratio, because having only augmentation interval long and short sampling interval short also makes no sense. And just repeat this until you get meaningful pictures on the current snapshot. Actually, this was worked in very many cases. It worked on my client and also some people who asked questions from the community. Nevertheless, this is, of course, time-consuming and repetitive for different workloads. And even though you find optimum sampling and augmentation intervals for your workload right now, who knows that will still be optimum 1 year after. Anyway, this guideline was added more than 3.5 years after DAMON has been merged upstream. I admit my mistake. I'm sorry about that. But anyway, I'm trying. And I was thinking that, yeah, the guideline is not very difficult, though. So maybe we can automate. And therefore, we have implemented the auto-tuning feature recently, motivated by the quarters auto-tuning. That is, we found that we are asking similar poor question like we were asking to DAMON's quarter users. We are asking what intervals you want. It is a kind of mechanism question, how to do. When should we do this, and when should we do that? Rather than that, we have a clear goal that the users would want to achieve, the meaningful amount of access events in each of the snapshots. And therefore, we let users to specify desired amount of access events to capture in each snapshot, and minimum and maximum sampling intervals, very similar to DAMON's quarters, right? And then, DAMON can find proper sampling and augmentation intervals for the desired amount of access events in each snapshot using the feedback loop again. If less than the desired events are captured in the last snapshot, then increase the intervals and vice versa. And the minimum and maximum sampling intervals are working as a safeguard of the resulting intervals so that the auto-tuning doesn't go too long way out of the grid. And this feature is now available on mainline from 6.15, so very recently added. And this might give you a question about, but this means that we have to add some more parameters. Why are you adding parameters for reducing parameters? That's a really silly thing, right? But we believe that these parameters are relatively easy to set. We have a good suggestion at this time. That is, for sampling and augmentation interval, we had default 5 milliseconds, 100 milliseconds, but those were never a suggested set. Now we have a suggested set for auto-tuning parameters. We suggest to have 4% of maximum events that can be captured in snapshot as the desired amount of the access events per snapshot for the auto-tuning feature. This is based on the applying Pareto principle twice. That is 20% of 20% means it can capture 80% of 80% outcome. I don't really confident about whether this makes sense, but in my test setup, this works very well. And also, minimum and maximum sampling intervals could be 5 milliseconds and 10 seconds, just a naive set. And also, the sampling to augmentation intervals ratio could be 1 to 20, in my opinion, because it's just a rule of thumb. Based on my test setup and based on my experience from production usage of DAMON, 1 to 20 worked in most cases. So how this works on real-world server workload? So we have run DAMON with the auto-tuning feature on a real-world server workload and monitored whether it works as intended by seeing how the sampling interval is changing over time on left side of the slide, and how the internal feedback loops measuring score also changes over time, as shown on right side of the slide. So the minimum sampling interval was 5 milliseconds, and maximum sampling interval was 10 seconds, and the auto-tuning feature was starting from 5 milliseconds and then adapting the sampling intervals as workload changes the access pattern, but it was converging to about 370 milliseconds on this real-world workload. And also the real-world workload was having busy time and non-busy time, and as the workload changes the phase, it was changed the converged sampling interval time from 300 milliseconds when it was busy and 4 to 5 seconds when it was very idle. Also, the tuning score also converges to the aimed goal. Also, we have ran DAMON-based monitoring on several workloads that are serving for real-world workloads, and we were always able to see meaningful access patterns and for the different workloads. And among those, there was a 1 terabyte memory size workload too. So as we initially said, the monitoring overhead of DAMON is not really ruled by memory size. It can scale regardless of the memory size, at least up to 1 terabyte, because that is the biggest machine that I have tested so far. Also, the auto-tuning of the intervals is not only for accuracy, but also overhead, because the sampling intervals are also increasing together, and DAMON does nothing between sampling intervals. And what we found as a monitoring overhead on this test was that with PS utility, the CPU usage of DAMON was always just 0.0% single CPU time. Of course, it shouldn't be 0, but the PS was accounting only to 1 digit on the point, and that was the research. And we further introduced a new recommended way for system-wide access monitoring based on this as a kernel module named DAMON Stat. This is a new kernel module that running DAMON for the entire physical order space of the system by default, and it utilized the intervals auto-tuning with the suggested parameters values. And it extracts a very simplified DAMON access pattern information, including idle time percentile. What is the idle time percentiles? Idle time is how long the region or the byte kept being not accessed at all. That is, access frequency was 0. And idle time percentiles is the percentiles of the sorted per byte idle times. For example, when it is unsorted, it will look like this. If we sort those by access frequency, it will look like this. Then we can show the sorted idle times as a length of the black bars, right? Black bars are 0 access frequency case. So we can see 50th percentile, 75th percentile, and 99th percentile idle time from this graph. DAMON Stat provides this information. And also, in addition to that, it also provides estimated memory bandwidth. And this is a recommended way for system-wide access monitoring if you want to start from very simplified, but most of the time just working access monitoring feature. It is easy to enable. You can enable that in build time, or boot time, or run time. Of course, you can also disable that in those times. And also, these two metrics are easy to aggregate and compare with others. For example, this is an example of the memory idle time percentiles on a real-world workload. We show that it has very small hot memory, and the idle time is increasing very exponentially. Note that the y-axis is in log scale. And using the DAMON filters, we can also do this monitoring in very fine-grained levels. We can show this distribution of the idle time percentiles for active pages and inactive pages on different array lists. This shows us that there is a room to make active pages more hot. And also, we can further break down this information for anonymous pages, fileback pages, unmapped pages, huge pages. When we use huge pages, we want huge pages to be hot and frequently accessed. Is it true on your system? You can show that. So that's all the technical part I wanted to discuss today. And just for your more information using DAMON. DAMON has merged into the mainline starting from 5.15, and many distros have backported that to their kernel and also enabled that. And also DAMON user space tool is also widely available. And there are kernel API. If you are a kernel programmer, there is DAMON sysfs interface if you are sysadmin. There is also DAMON user space tool that you can use. And also there are some DAMON modules that are specially optimized for a given use case, like DAMON status for basic DAMON, basic system data access monitoring. And we have community. We have public mailing list called DAMON. We have a bi-weekly virtual meetup. And we have project website that has every resource that you should need. If there is something that's missing there, please let me know. And also, if you are not used to mail-based code review or patch submission or discussions, we also have our own tools for helping that called HKML. Not only for DAMON, it is also for general Linux kernel developers, but because I am developing that and maintaining that, if any DAMON contributors have problem with that, I will prioritize that. And the future of DAMON is, of course, open and up to you, because like any other kernel subsystems, and like this case, we are preferring random evolution. That is, if it was intelligence design, the auto-tuning of the intervals should be done in very early days, but because of the random orders, it has been made pretty late. I'm sorry about that, but I'm trying to do better. So yeah, so summary, that's DAMON. DAMON is a kernel subsystem for data access monitoring and access aware system operations, and it can be safely controlled and self-tunable. So please try again if you didn't try the auto-tuning and control features before. Please give us one more time, one more chance. And yeah, finally, the future is open to you and up to the community. So if you have anything you want, please make your selfish voice. We have 3 minutes for Q&A. Thank you. Yes, please.
First question. You mentioned that it's possible to add tracking wide granularity. So, but my worry, how huge will the statistic in this case? Can available memory keep these statistics? So how huge it can be?
So the question is how huge the dynamic size region can be. And it could result in poor accuracy when the memory is pretty big and there are so many different access patterns, right?
Not exactly. I mean that if we are like tracking byte granularity, let's say we are tracking 64 bytes, not 4K or maybe more. So in this case, statistics should be bigger, I believe. So will it be enough memory to keep all of the statistics that DAMON needs to use?
You're right. So the question is, if we want to do byte granularity monitoring, then DAMON would need to have much larger metadata, and that could be a problem. I agree with that. And yeah, and therefore we currently don't support byte granularity monitoring at the moment. And nevertheless, users can set the minimum and maximum region, number of regions. And by setting those the same, users can do fixed granularity monitoring too. And for byte granularity monitoring, it is also available if they have enough memory to keep the metadata, but that's up to the user's choice. They could do page granularity monitoring, or say huge page granularity monitoring, or 1 gig huge page granularity monitoring, or multi-site huge page monitoring, but that's up to the users.
Second question, you need to keep statistics in memory too, and DAMON need to operate by these statistics. So how you distinguish that, for example, we are tracking some application, like how application access memory. For example, how to distinguish daemon memory from application memory? Because we don't need to track like daemon activity.
Good question. The question was, so daemon also has metadata for itself, and daemon will do access to each metadata. How we distinguish the access to daemon's metadata and the data for real monitoring, like the memory from the user space workloads? The answer is that daemon can capture access to memory for users only. That is, daemon cannot see the access to kernel memory. And daemon's, in this question, daemon's metadata is stored in kernel space as a kernel memory, and therefore it will not show access to daemon metadata. It will just show like unaccessed. Any other question? Yes, please.
Yeah, and just mention about the daemon page up, right?
Can you please come again?
I mentioned that in one slide you mentioned that in situation that daemon might trigger the page up for the whole page, right? So I was thinking about what's the relationship between daemon page out and the kernel thread case swap D. So would you like to just want to avoid the situation there where when the system memory is short and the kernel subsystem maybe will trigger the slow case location, which in turn trigger the memory reclaiming and case swap D, and finally all and here to be triggered. So it looks like your purpose is try to proactively to swap out the core memory to the swap space. Am I understand correct?
You're right.
Okay, cool.
So the question was how daemon-based memory reclamation would work together with existing memory reclamation schemes like direct reclaim or K-swap-D. And the daemon-based reclaim is, in most cases, just only for proactive usage, and therefore it works only when the system is having modest level of memory pressure store, rather than in catastrophic case that K-swap-D wakes up or even direct reclaim starts and eventually kill starts. So it depends on, of course, the use case of the users. In some case, users might want to use daemon to really replace K-swap-D or even direct reclaim, but to my understanding, to my best knowledge, most of the users are using daemon-based reclaim only for proactive use case.
Okay, so this feature can proactive to swap the whole memory to the swap instead of the K-swap-D, so that the memory system have the enough memory for the upcoming memory allocation requests, right?
I'm sorry, please come again.
Oh, I mean that you, with this feature, it can get the benefit for the kernel memory subsystem to get efficient, to get enough memory for the upcoming memory request, so that the memory subsystem won't trigger this slow pace memory allocation. So this is the advantage of this one. Cool.
The question was whether daemon-based reclamation can also help existing kernels reclaim features like K-swap-D by proactively reclaim cold pages so that the system will have more free pages that help resulting kernels page allocation easier. And yes, if we do daemon-based reclamation, then it could help such a case, I believe. And also we are working on making such a daemon features for helping existing kernel memory management features, like finding hot and cold pages in the system and putting those in LRU active and inactive list if they are mislocated on, say, hot pages on inactive list or cold pages in active list. Those should be swapped. DAMON can do that. So yeah, such a case could be developed, in my opinion. Okay, so I think we are already 5 minutes over time. If you have any question, please reach out to me on hallway tracks or here. Thank you very much.